Hey, what's up, everybody? As promised, I'm going to go through homework number 3 here. I'm not going to solve like the whole thing, right? But I just want to show you kind of what you're supposed to do for most of the problems. So, number 1, um, let's see here. For this one, this is pretty straightforward, right? 3 resistors in series. It's just going to be REQ. It's going to be R1 plus R2 plus R3, and if you use the convention for the symbols that I specified, that's just going to be R plus 2R plus 3R, right? Which should be 6R. So that's cool. B is a little bit more complicated. What we need to do is we just need to figure out what the equivalent resistance is between the 200 and 300 ohm resistors, right? Because they're in parallel, and then add that in series to the other one. So this is going to look like, we could write it like this. We could write, this is R for the 100 ohm one, and then we could write something like R 2/3. So it's going to be R plus, and then we have to do this reciprocal thing. So it's going to be 1 over 2R plus 1 over 3R, all to the negative first. And I'm just going to have the computer tell me what that is. Hope it'll simplify things nicely. So it should be 11, yeah, that's perfect. It should be 11/5 times R. Okay, there's that. And then the last one is a little bit, let's see here. This last one is a bit trickier. But what I would suggest you do is you focus on the fact that this 200 and 300 ohm resistor are in series with each other, right? So we could write something like this. Maybe we could write R2/3 is going to be 500 ohms, otherwise known as 5R. And to figure out the equivalent resistance in the middle, let me just call that R, I don't know, M for middle or something. It's like, now it's like we have 2 500 ohm resistors in parallel with each other, right? So to figure out this, we just do 1 over 5R plus 1 over 5R, all to the negative first. And this should just be 2 over 5R to the negative first, which is, of course, going to be 5/2 R. So then our total resistance here, or equivalent resistance, is going to be R plus 5/2 R plus R. Right, so that's what, 4/2 plus 5/2 should be 9/2. And that's 4.5 times 100, right, for the equivalent resistance there. Let me just double check this. So 2 over 2R plus 5 over 2R plus 2 over 2R. Yeah, 9/2. Okay, cool. So doing it with the capacitors is a little bit more obnoxious. Hopefully, like, I don't know, people maybe don't need me to go through and do this for the capacitors, because remember that we add capacitors in series the way that we add resistors in parallel. So like for number 2 here, maybe at least start the first part, what we would find is that the equivalent capacitance here is going to be 1 over C plus 1 over 2c plus 1 over 3c, all of the negative first, right? And you just have the computer tell me what that is. That's 6 over 11 times c. So whatever that works out to be, right? Taking c to be 100 microfarads. The next one isn't, I guess, actually that bad because we have the 200 and 300 microfarad capacitors in parallel, and capacitors in parallel are actually easier than capacitors in series, right? Because we just straight up add them. So let's do this. We'll say maybe like C2/3 is equal to 2C plus 3C, which is 5C. So then our equivalent capacitance in this case is going to be 1 over C. We have to do this thing again, because now we have basically the equivalent capacitance between the 200 and 300 microfarad capacitors in series with the 100 microfarad capacitor, right? So we have to add the reciprocals again. So we're going to do this. We're going to do 1 over C plus 1 over 5C. And this should be like 6, well, to the negative first, right? And this should be 6/5. Is that right? 6/5 to the negative first. No, 6 over 5C. Okay, my bad. Yeah, 6 over 5C. So 5/6 C. Let me just double check this because I can't be trusted to do the addition of basic fractions. Okay, well, I guess maybe I can, but it's good to check. Okay, so 5/6 C for B. Now, C is the kind of obnoxious one here because you have to add the 200 and 300 in series, right? But notice that there's also a 200 and 300 down here. So I'm not going to do this. I'm just going to talk about what you do here. I would say add the 200 microfarad and 300 microfarad capacitors in series. So I guess we can do this. We'll say that the equivalent capacitance here, let me call this, I'll call it CM, I guess, again, for just the middle, because I'm going to want to write the equivalent capacitance is the equivalent capacitance of the whole thing, right? So I'm just using an intermediate symbol. So I have to do this. I have to do that this is 1 over 2C plus 1 over 3C, all to the negative first, right? And I want to say that this should be like 3/6 plus 2/6, so 5/6 again. Does that sound right? I think that's right. I'll just double check though with the computer. So 1 over 2 times C plus 1 over 3 times C. And also, like, if you're doing this on a calculator, right, like a TI or something, during the exam, you can always just like omit the C's and then stick it back in at the end, right? So I could do something like just add 1/2 and 1/3 here, and then raise that to the negative first, and then just put a C back in at the end. So you can also just do this on a calculator, but I will include the C's here because I can. So this is 6/5. Okay, now combining this like path here, this branch, these two capacitors with these two is fine because it's just going to be, so we'll call this C big M now because I don't know what else to call it, but it's just going to be double C little m, because remember that capacitors in parallel add like resistors in series. So it would just be 6/5 C plus 6/5 C. So this is 12/5 C, right? And then the last thing to do then is to find the equivalent capacitance, which is going to be adding reciprocals, right? And we're going to do this. We're going to say 1/C plus, this is 12C over 5, so 5/12C plus 1/C, all to the negative first. I think that's good. Let's just crank that out real quick. Based on the questions that I got during office hours, actually, this was like one of the ones that people were most unsure about. And it's probably just the algebra, and I don't want to, make you do any disgusting algebra on the exam, but I had to torture you a little bit, right? So it should be 12/29 C. Nope, C, like that. I mean, there's a chance I'm making a mistake here because I haven't really looked at this or worked through it before, but I think the approach here is good, right? You just want to remember that for resistors in series, you just straight up add the resistances. For resistors in parallel, you add the reciprocals, then take the inverse, right? For capacitors in series, you add the reciprocals and then take the inverse. And for capacitors in parallel, you just add them up, right? So you just got to really remember that the rules are opposite each other. Okay, so I actually ended up doing the whole thing. That's fine. It wasn't that bad with the help of Mathematica. Okay, so let's see here. I had you simulate this circuit, but I will talk about at least setting this up, right? Because you won't have the simulator for the exam. So let's just kind of talk about how you might set this up. And I think the big thing, I think people are okay with like Ohm's law and stuff like that, but it seems that maybe people are just a little uncertain about adding, or rather how to specify their currents. What happened there? Let me try this again. Okay, let's make this a little bit bigger. Should be fine, probably. Okay. What the? Why? Well, okay. Let me try this one more time. I'm just going to zoom in. Okay, so we want to draw in what we think the current looks like, and I will start probably bottom left corner because that's where I usually like to start. We'll draw in one loop or one path of the current, I guess. And I'm going to say that here the current looks like this, right? And we call this I1. Now, I know this is incorrect because I've looked at this, but what I'm going to do is I'm going to make a bad assumption here, and I'm going to assume that the current splits, let's say like this. So some of it goes off into R2, and then some of it goes off into R3, like so. Now, quick sanity check, right? I should have that here, and here I get the same equation for my continuity of current, right? So let's just write out what that is, and let's say top node, I find I1 equals I2 plus I3, right? And maybe most of you, or maybe even all of you, can already see this, but I think it's a good idea just to make sure that you're being consistent to check this. And in the bottom node, right, I also find that I2 plus I3 should equal I1. And that's good because I get the same equation, right? And, and maybe a simple way of thinking about this is like water flowing through pipes. Like whatever goes into this node is going to split here, maybe depending on, say, if we're thinking about water, like depending on the diameter of the cross-sectional area of the pipes, right? And then it's going to meet back up here, and we should have the same amount of current that we originally had. And I know that this is a bad assumption. Well, actually, I think I remember that this is a bad assumption because I do believe the current actually goes around this way, out of this battery instead of into it. But that's fine because we'll see what that looks like. And, you know, odds are that you won't necessarily be able to know what the direction of the current is just by looking at the circuit right away, right? So my first loop, I'll just specify this verbally. My first loop is just going to go from the corner, the bottom left corner, through R1, down through R3, and then back to the corner, right? So for my first loop, I'm going to have this. I'm going to have we go up by E1, right? Because we're going from the low potential terminal of the battery to the high potential terminal. We drop by I1, R1 because our loop is going in the same direction as our assumed current, right? And then again, we drop I3, R3 across resistor 3 because we're still going in the same direction as the current, or the assumed direction of the current, right? And this is 0. Now I will do the outer loop, which will start at the bottom left corner and then go up through the battery through R1, through R2, and then down through this battery and then come back to the corner, right? So the first two terms are going to be the same. We go up by the EMF of the first battery. We drop by I1, R1 in the second battery, and then we drop I2, R2 in the second resistor. Now, our loop is also oriented so that we're going from the high potential terminal of the battery to the low potential terminal. So we're going to drop here by the EMF of the second battery. And then from the low potential terminal of the battery all the way back to the bottom left corner, which is where we started, there are no components in the circuit that we're hitting, right? So there's nothing going on after that. And so this is two equations, right? We have 3 unknowns if we want all the current. So our last equation is going to be just the conservation of current equation that we already wrote, right? So this is going to be I1 equals I2 plus I3. Now, what I would suggest you do if you want to use your calculator to solve this is go through and write all the equations out very carefully. And I'll show you what I mean by this, right? So I'm going to take my first equation of those 3 up there. Let me just make this look nice. I'm going to take my first equation now, and I'm just going to rearrange things. I'm not really writing anything new. I'm just taking the equation and making it easier for me to put into my calculator when I go through and I do the matrix stuff, right? So I'm going to write minus I1, R1, and then I'm going to put plus 0 because I want a placeholder for where the I2 term would be. But there's no I2 term here, so I'm just going to write plus 0. And maybe you'll see why I do this when all the equations are written out. And then I'm going to have minus I3, R3 here, and then I'm going to subtract the EMF of the first battery from both sides. And this is kind of the form that I want to put all my equations in, right? I want all the currents on the left-hand side, and I want everything else on the right-hand side. So there's that. Then we do the same thing with the second one, and I could write this minus I1, R1, minus I2, R2 plus 0 equals, and now we're going to have E2, right? We add that to both sides, minus E1. And then the last one is pretty easy because it only has I terms. It's going to be I1 minus I2 minus I3 equals 0. And notice that this is mathematically equivalent to the third equation on in the top set, right? So we get this. Now I'm going to make a matrix out of this, and what we do is this. We do how do I say this? We just put the coefficients in the matrix, right? We make an augmented matrix and we put the coefficients in. So my matrix is going to look like this, and I'll zoom in on Mathematica in case it's hard to see. My matrix is going to look like this. So minus R1, 0, minus R3, minus E1. It's my first matrix, or my first row of the matrix. Let me make sure I got it correct. Okay, cool. My second row is going to be minus R1, minus R2. And I know that the syntax here might not look or might not be clear to you. So what I'm going to do is after I put this in, I'm just kind of talking to myself right now. I'm going to have Mathematica output it as a matrix so you can see what it should look like. So just bear with me for a second while I get this set up. I want E2 minus E1. So we're going to have a 3x4 matrix, right? We have 3 equations and 3 unknowns. And so then the last one is just going to be, this is the nice row. It's going to be 1, minus 1, minus 1, 0. Because remember that when we write our matrix out, we're basically just suppressing the I terms, the I1, the I2, and the I3. And that's going to work just fine for us as long as we get the matrix set up properly with all the coefficients in their correct places. And that's why I think it's a good idea to write your equations out like this, so you can kind of very easily transfer this information into your matrix. So I'm going to check this one more time just to make sure it looks good. So minus R1, 0, minus R3, minus E1, minus R1, minus R2, 0, E2 minus E1, 1, minus 1, minus 1, 0. Okay, and then I'll tell Mathematica, hey, show this to me as a matrix. And I'll zoom in a little bit maybe. That makes it easier to see. So then I have a matrix set up, right? I have minus R1, 0, minus R3, etc. And so this is the matrix that I want to solve. And so I think, how do I do this in Mathematica? Is it row reduce, maybe? I'll have Mathematica row reduce this, but you're going to use the RREF thing in your calculator. And then I'll have it output it as a matrix. Okay, that's gross, but I can get numbers at this point. And this is what you'll do, right? So, okay, so this is what I'm getting. This is like my first current. This is my second current. And this is my third current. And I would trust that this is what you're going to get if you actually go through and you do this by hand, which is why you don't want to do it by hand. But what you can do is you can just tell, now at this point, right, what I can do is I can just tell Mathematica what the numbers are. So I'll just do this real quick. I need to look back at the assignment. So R1 is 4, R2 is 5, R3 is 10. And obviously you can't put symbols into your calculator, right? Unless maybe you have like a fancy like TI-89 or something. And that's fine. I don't expect symbolic solutions for stuff like this because this is, 3 equations, 3 unknowns. So 5, and then 2 is 2.5. So let's see what we get here. Let me plug the numbers in. And then I want this. So it actually looks like I guessed my current directions correctly. And actually, yeah, I did. Because you know what? I would actually probably, if I hadn't seen this problem or had people asking me about it, I probably would have made my I2 actually go around this way. So that would change my continuity of current equation. But it's fine because I would have just wound up with a negative number for one of my answers for the current, right? When I do this, and this is what you would see in your calculator, basically this exact same thing. And I would have then just realized that, okay, I made a bad assumption for one of the directions of the current. And so if I needed to specify that for my answer, I could always just write on my exam, for instance, oh, I guess the wrong direction. It actually is going the opposite way or something like that, right? Just something to indicate that you made a bad guess. And it happens, right? It's probably, unless like you're like an electrical engineer or something, it's going to be pretty hard to look at a given circuit and know which direction the current is flowing in every part. And I just realized that maybe the camera thing is blocking, but this is what I did, right? I think this is probably only an issue for like the upper part of the circuit, but I just went around this loop, and then I went around this outer loop, and then I used my continuity of current equation, and good to go, right? Okay, cool. There's that. And then you can always simulate this too, right? Just to check your answers, make sure that you did the problem correctly. I'm not going to do that. I think probably everybody knows what how to use the simulator, so we'll skip 4. Number 5 is, it was meant to be easy. I just realized that I I shouldn't say I realized, people told me that I forgot to give you a current, which you needed, and I think I said like 22 milliamps or something like that. So let's just look at this one really quickly. Let's see, how do I do this? I'll make this circuit, I guess. Or I'll just use this to draw what it might look like. So what we have here is we have like two situations. We have essentially a DC battery, right? Like this, which would just be the battery if it read 9 volts. But what's actually happening is we're reading less than 9 volts when we measure it, right? With some known current. And so what we're gonna do, okay, it's bothering me that it's not horizontal. Just bear with me here. I know I have problems. It's okay, I've accepted it. So we're gonna add a resistor though, and this is gonna essentially model the battery, right, with some bit of internal resistance. So it's like up here on top, we have sort of the ideal case where if I measured the voltage from this point to this point, I would find 9 volts, right? But it's like what's actually happening is I'm measuring the voltage from this point to this point, and I'm finding 8.8. And so I have to account for that with a little bit of internal resistance. So let's see what we would write here. We would want to write something like this, and I'll say that V is the voltage we measure, and I think this is a pretty common convention. E, or script E, is the voltage of the ideal battery, right? So what we're going to say then is we're going to say that essentially V equals E minus I R, and it's conventional to use a little r for the resistance of, or for the symbol for the internal resistance of a battery, right? That's like what the textbook would do. And it kind of makes sense because it's not supposed to be very big in general. So all we have to do here is a little bit of algebra, right? We just rearrange this equation. And I think I told you to use 22 milliamps for the current. So that's what I'm going to do. I'm just going to write IR equals, we add IR to both sides. We subtract V from both sides. I think that's good. And then we divide both sides by I, right? So we find that R is going to be the EMF minus the voltage we measure divided by the current that we're running through it. And we'll get a number here. So the thing is, we should expect this to be a positive number, right? Because resistance is essentially always positive. And so we'll just crank this out. We say 9 minus 8.8, and then 22 times 10 to the negative third. Incidentally, you're going to want to be sure that you're very clear on what all these prefaces mean, right? Like milli, nano, micro, whatever, for the exam. I don't mind telling you, I guess, if you don't have it on your equation sheet, but remember that just takes time for you to ask, and it probably would be better if you just have them all written down. So anyway, let's crank this out. We get about 9 ohms, which is fine, right? We wouldn't expect it to be probably like kilo ohms or larger because, in general, these internal resistances are small. I mean, if they're not small, then it's a shitty battery, right? And so I think this is reasonable, and this is kind of what I was hoping you would do here. Okay, I almost stopped to ask if there were any questions. Teaching this class is making me lose my damn mind. It's not your fault. It's just a lot. Okay, so let's look at 6, because 6 here, 6, I think, kind of presented challenges for lots of people. And it's understandable because, like, I told you in class, right, that personally, capacitance is confusing to me. I mean, I'm doing my PhD in this stuff. And I do have a good deal of exposure to this topic from before. It's just still like a very weird thing. So let's look at this one and try to make it all make sense. So I think that the charge on capacitor 1 is not bad at all because let's say this. Let's say C1 is in parallel with the battery, therefore, and let's say it feels the full potential difference. And what this means we can do is we can write something like this. We can write from the definition of capacitance, right? Remember we said it was a proportionality constant that takes us from a voltage to a charge. We can write this. We can write Q1 equals C1V, where V is 10 volts, right? And this then tells us, well, actually, this is all we need to do, right? We don't even need to rearrange this or anything because we know C1 and we know V. So we've got the charge on capacitor 1. So this isn't bad at all, I think. The other part is much trickier though, because we have to, maybe do some things to figure out what the equivalent resistance is, and then we have to reason, maybe using the loop rule. That's probably how I would approach this, like about the potential differences on the capacitors or the equivalent capacitors, right? So if we call the capacitor below C2 C3, right, then what I would do is I would say the equivalent capacitance of C2 and C3, and I'll just say this, the capacitor below it, capacitor directly below it, below C2. Just so we're clear, we're talking about the same thing. We have to find this using the addition rule for capacitors in series, right? So we'll call this C2/3, and this is going to be 1 over C2 plus 1 over C3 all to the minus first. Now, this problem does kind of suck, but one of the nice things at least is that all the capacitances are the same, right? So that does help a little bit. And what we're going to do is we're going to write finally that this is 2 over C all to the negative first, otherwise known as C over 2, right? C over 2. So that's that. Now, let's see here. So what we want to also realize is that the charge for capacitors in series is the same, right? So we're going to think about the potential difference across, let's call it C4, which is going to be this one, and C5, right, which is this one. And so let's just not think about this for a little bit, and we're gonna go into a separate analysis here, just thinking about the loop rule. So we're gonna start below the battery, right? And if we do that, we go up by V. Then we're gonna drop by the voltage across capacitor 4. We'll call that V4. And then we're gonna drop by the voltage across capacitor 5. We'll call that V5. And this should be 0. So what we find is V4 plus V5 equals V. And we know that the voltage across 2/3 is the same as the voltage across 4. Because remember that this is 2/3 and this is 4. And so we want to figure out what the voltage across 4 is. Now, these, let's see here. So, yeah, we want to figure out what the voltage across 4 is. So the way that we could do this is we could say something like this. We could say, wait, what do we want to do? Maybe we actually want to Maybe we think about the loop rule the other way too. So we go up by V, right? If we start below the battery, and then we drop by V2, we drop by V3, and we drop by V5. We're back at 0. But because, let's see, because the capacitances are the same, and they're in series, we know the charge on them is the same. We know the capacitance is the same, so we know that V2 equals V3, right? So we could write something like this. We could write V minus V2, or 2 rather, 2V 2/3 minus V5 is 0. And I don't want to make this a stacked fraction. Okay. So there's that. Now let's think about this. I don't think I like this notation because it's kind of conflicting. Geez. What do we do here? I hate capacitors. So we found the equivalent capacitance of these two. We know the potential difference across these two has to be the same as the potential difference across this one. And we know that the potential difference across this one and then across this one has to add up to 10 volts, right? I think maybe what we want to do is actually find the equivalent capacitance of this whole thing here. So let's just do that and see if that's fruitful. Okay, so to find the equivalent capacitance of, sorry about that, to find the equivalent capacitance of 2, 3, and 4, remember I'm saying 4 is this one, we could write this 2/3/4, and let me fix this real quick, 2/3/4, no, I want linear fraction, is going to be, now this isn't so bad because we can just add the capacitances, right, because they're in parallel, so it's just going to be C over 2 plus C, which should be 3/2 C, right? Now, this equivalent capacitor, let me just put this in words, the equivalent capacitance between 2, 3, and 4 is in series with C5. All right, remember 5 is this one. So the charge is the same, right? So what we can do is we can say something like this. We can say Q5, right? This would be the charge on 5, is the same as C1, or sorry, C5. And then let's just call it V5, I guess. Or let's just call this Q for simplicity. But we also know that Q is C2/3/4. And then it's just the voltage drop. Let's say the voltage drop across 4, because we know that the voltage drop across 4 is the same as the voltage drop across 2 and 3, right? So we can write something like this. And so what we could do is we also finally want to note maybe that V4 plus V5 is just V, which is V is the total voltage of the battery. So we could make a proportion here. We set Q equal to Q, and we can just write that, let me do this, Q equals Q which says that C5V5 equals this. Okay, I think we're getting somewhere. And then we would finally want to note that if we want V5 or V4, it doesn't really matter. We can just make a substitution based on this. Because we find that, let's say, V4 is V minus V5, right? And so then we can plug that in for V4. We can write this equation one more time. We can say C5, and I'm going to simplify the notation here a little bit, because again, remember all the capacitances are the same, so I'll just write C here for C5. And then we can say that this equals what we found for 2/3/4, which was 3/2 C. And then we can multiply this by V4 is big V minus V5, right? And so we could solve this for the voltage 5, and notice that we can just cancel the C on both sides. And I'll make Mathematica solve this for me really quickly. We'll say solve V of 5 equals 3/2 times V minus V5. We want this in terms of V5. And so it's 3/5 V. So this equals, we find that V5 is 3/5 V, which should be, what, 3/5 of 10, right? So that's 6 volts. Hello? This equals 6 volts. Okay, I honestly don't want to mess around with this one too much more, but what I'll just say is this. So we now know the voltage drop from here to here, right? We know that this is 6 volts. So we also know that the voltage drop from here to here across C4 must be 4 volts, right? Because 4 plus 6 is 10. And we also know that the voltage drop across each of these capacitors, because they're in series and they have the same charge and they also have the same capacitance, must be the same. So the voltage drop from across this capacitor and then across this one must add up to 4 volts, or technically negative 4 volts. So we know that the voltage on each of these is 2 volts, right? Because we would have to do a loop, and we would go around, we go up by 10 volts, we go through this path, we drop by 2 volts here, we're now at 8, we drop by another 2 here, we're now at 6, we drop by 6 volts here, we're back to 0. So it works. So this is a little bit convoluted, but the reason I do it this way with the loop rule is because that just makes more sense to my brain. But you could also, I don't know, I'm sure there's another way to do this. But this is what I would do. And now that we know the voltage across the capacitor and we know its capacitance, finding the charge is not difficult, right? So hopefully you feel better about this stuff than I do, because like I said, capacitors are confusing, but you can sort of reason your way through it, right? And if there's a capacitance problem on the exam and you decide to do that one, maybe because you don't like magnetic fields or whatever, then you should have a lot of time to be able to think it through, right? So hopefully people aren't feeling too anxious about that. Let's talk about 7 just very briefly, I guess. So what we want to do here is we want to use this formula that C is epsilon naught A over D, right? This is our equation for the capacitance of a capacitor that has vacuum between the plates, right? So we'll just say no dielectric between plates. And then we want to also write that, we'll write something like this. We'll write C as a function of kappa. Now we're talking about a dielectric is going to be just kappa epsilon naught A over D. And this is with dielectric between the plates. And all we have to do here is for like part A, we just apply that formula, right? We write this, we write C is epsilon naught A over D, and the only thing we have to do is we have to write the area in terms of the diameter, right? But the plates are circular, so our expression is going to be this. It's going to be epsilon naught pi. Let me use like a script R just in case. I know there's no resistance in this problem, but I do want to keep the symbols separate, I guess. So this is epsilon naught times the area of a plate, right? But R, the radius, right, is just half the diameter. So we do this. We just put D over 2, quantity squared. And then you can go through and you can algebra it up, simplify it, right? But actually you don't even need to. You could just plug it into your calculator like this and that would be fine. So then to get the charge here for part B, we simply write Q equals CV. We found C. It was this. And V is given. It's just 120 volts. Yep. So you just crank this out. Good to go. All right, let's talk about C very briefly. For C now, it's like we have V prime. V prime is 100 volts, right? And we need then to write something like, the charge is the same, right? So we can write this. We can write Q equals CV, which also equals C prime V prime. Because the charge is intended to stay the same, right? Now CV is this. We just found that. And then C prime is just going to be this thing. It's literally just going to be the capacitance with a dielectric inserted, right? So we can substitute that in over here, and we'll just make the substitution for A again, which was that it was D over 2 quantity squared. We also have to remember to put in a pi, I guess, for the circular plates. And then we put V prime. Right, so notice that lots of things are going to cancel here, which is very nice. We're not changing anything about the dimensions of the capacitor, right? So we can just get rid of this whole D over 2 quantity squared thing on both sides. We can get rid of the pi. Like that, we can get rid of the D's. We'll just call them 1. And we can also get rid of the epsilon naughts, right? So we should find essentially that V, which is 120 volts, it must equal kappa V prime, right? And that makes sense because the only thing we're changing about the capacitor is we're putting a dielectric in. And so maybe you could see this, without going through all the work that I did, but, to show it carefully and methodically, you'd probably want to do what I did. And so we just can write that V equals kappa V prime, which then tells us, right, that kappa must equal V over V prime, and that's going to be 1.2. Right, 120 divided by 100, yeah, I think that's 1.2. Okay, cool. Let's talk about 8. I don't think 8 is that bad, but we didn't really do any examples or anything with the power dissipation in a battery, or sorry, in a resistor, so it's probably a good idea to work through this. So we have that a resistor of unknown resistance is connected between the terminals of a 3-volt battery. Energy is dissipated in the resistor at a rate of that. Okay, so I'm going to change the notation really quickly here. I'm just going to write P instead of R because this is a power. It's also a rate, right, of like energy dissipation, but we'll just call it P. Okay, so it's 0.54 watts. Now the Joule heating law. Heating law says that P equals, says a lot of things, right? It says P equals IV equals V squared over R equals I squared R. I think these are all correct equations. Check the textbook or your notes or something to make sure though. And we want to basically try to do this so we don't have to do more work than necessary. Right, so I would focus on this. I would write that P equals V squared over R. So we have the power, which is 0.54 watts. We have the voltage of the battery, which is 3 volts. So this allows us to solve for the resistor, right? Which means that the resistance must be multiply both sides by R, divide both sides by P. It should be V squared over P. And we don't even need to solve for this. Like, we don't need a number because we can just keep going symbolically. But this is our resistance. We didn't know it to begin with, but now we know it. So then we want to just do this again. But what we want to do now is we want to write something like this. We want to say that the resistor, we'll say P prime, okay, which is the new power that we want to solve for. This is the rate energy is now being dissipated at. And we want to write, well, V, the new V is 1.5 volts. Remember, before it was 3 volts. So we could just do this. We could just write V over 2, quantity squared, because we're having the voltage, right? And then from the form of the Joule heating law, this is R, right? But we also know that R is V squared over P, which is the original power, which it's the 0.540 watts, right? So you go through and you just crank this out, you know, do the algebra, and you would get some value of power. And so you could also, you know, you don't have to necessarily do it this way. You could just get a number here and then go, but I want to show you as much as I can what it's like working symbolically, because I want everybody to have a clear idea of what that should look like, at least according to my standards, which I think are pretty conventional. But yeah, so you just algebra this up, and then you would find the new power. I think this is good. Yeah. Okay, cool. Hopefully this was helpful. Hope everybody is feeling okay about the exam on Thursday. And, you know, if you have any questions, of course, definitely reach out to me, and I'll try to help you as much as I can. All right. Have a good day or night or morning or whatever it is when you're watching this.